Hello, everyone. Welcome to the next meetup organized jointly by quantum computing groups from Washington, D.C., Toronto, and Warsaw. My name is Pavel, and I will be the moderator of this event. I'm the CEO of the Quantum AI Foundation and also leader of the Warsaw Quantum Computing Group and Q Poland. I hope that second moderator, Dr. Sebastian Zając, will join us as well. Anyway, it's good to start and good to introduce our great speaker for today. Dr. Brett Green will tell us about Landau level phases of bilayer graphene. So it sounds very interesting. Before we start, we would also like to announce our next events. So in April, Eric Rater will tell about the serious challenge to quantum mechanics and its applications. And then later in April, we'll have a talk about QA HPC on the quest of quantum AI optimized HPC. And the speaker is Dr. Liwen Shi. Then in May, Dr. Bruna Araujo will tell about moving towards compactification of the many-body wave function using a bottom-up approach. Later in May, Edo Justa will tell about quantum reliability, circuit susceptibility, faults, and integration issues. And then in July, Zeki Seskir will tell us about educating to the culture of quantum technologies, a survey study of concepts for public awareness. Before we start, we would like to thank our partners and sponsors for supporting us. As you can see, there are several organizations involved. And yeah, I think that's all from my side. So I will now stop sharing my slides. And Brett, if you're ready, the Zoom is yours. And yeah, it's our pleasure to have you with us. Thanks for accepting our invitation. Maybe just one more announcement to the participants. We have agreed with Brett that this event can be interactive, so that if you have some questions, feel free to raise your hand and we'll try to interrupt and ask questions. But you can also post your questions on the chat, and at the end, there will be also time for Q&A session, hopefully. Okay, I think we can start.
Yeah, thank you very much for the kind introduction. So let's jump right into it. As Pavel said, I will be discussing Landau levels in bilayer graphene, but I'd like to start with a little bit of background. First, I want to discuss why it's of interest to do classical computing with quantum variables. I know that this is largely a quantum computing group, and we usually think about quantum computing with quantum variables, but there are also some reasons that would be of interest to do classical computing with quantum variables. So I want to share this complementary side of this, and then I'll dive into how Landau levels in bilayer graphene are a useful platform for classical computing with quantum variables. And I'll discuss more of what makes this an interesting physical system to study before leaving us with some future directions and related topics to think about. So first, very simply, why are we motivated to go to the next generation? We have good classical computers already. Well, one reason is size. As technology advances and we learn new ways of information storage, we can store information much more densely. A simple example is that you can fit about 2,900 copies of the collected works of Shakespeare in a single 16 gigabit flash drive. There's also efficiency. A limiting factor of current computing power is joule heating. So the resistive heating as you move electrons back and forth, you move charge across a wire. If you've ever talked about like overclocking a computer, you'll be familiar with this as a limiting factor, because there are cases where you can actually operate a computer more quickly at the risk of burnout. So it would also help to have more efficient electronics. And finally, also speed and reliability. Anyone who's used a calculator versus calculating by hand or with a mechanical tool knows that it's much faster and more reliable to use electronic computation. So that's a bit of a far in the past historical perspective on why we're motivated to move to the next generation. But now let's start thinking specifically about classical and quantum electronics. And very interestingly, there's already an example in the form of spintronics that we've used to advance hard drives and continue the miniaturization and the increase in data density in magnetic hard disk drives. The example here is known as giant magnetic resistance. So taking advantage of the quantum property of spin of an electron, if you have a bunch of magnetic layers that are all aligned, then a spin that is aligned with those layers can pass straight on through. That's indicated in this diagram here on the left. On the other hand, if those layers are anti-aligned, then a spin will not be able to pass through all of the layers. It might pass through the first one if it's aligned, but as soon as it encounters a layer that is misaligned with a spin, it will bounce off. And so in that way, you can use quantum properties to detect magnetization, which is very useful if you want to build a very, very small read head for a high density hard drive. But the story doesn't end here. There are also ways of using spin and spintronics to store information that are still in the future for us. One of these is what's known as a skyrmion. So if you have a bath, a material full of up-pointing spins, you can smoothly turn down spins into this topological feature where in the center, the spins are pointing down. And yet, if you look at each spin's neighbor, they are all still only slightly deviated from one another in their direction. And so there's this smooth, continuous transition, and there's no way to deform, to flip just one spin and have it be aligned with its neighbors. So this managed to be stable while still having a difference in the spins. And this is a potential next generation form of information storage that would be more efficient because it takes so much less energy to flip a spin than it does to magnetize or demagnetize a domain on a hard drive, or to move an electron on and off of a transistor. And it could also be higher density. But to build something like a skyrmion, we need to have quantum order. We need to have a system where all the spins have agreed to be upward. And this is in general a challenge. It's a challenge because of the Pauli exclusion principle. Pauli says that we can't have any electrons share quantum numbers. This is why if you look at an atom, you never have an atom that's all s orbitals. It's always s, p, d, and so on, filling up the electron shell. So the general, there is a way around this though. There is a way that we can still get quantum order in spite of the Pauli exclusion principle. We just have to learn to work with it. So continuing with the atomic example, I'm going to look at the electron configuration of manganese. You can see here that it's managed to get an ordered outermost shell, an ordered 3D orbital, where all spins have agreed to point up. So how do we do this? The first thing we need is an extra quantum number with negligible energy cost. In this case, that's the magnetic quantum number, which has 5 eigenvalues, and so we can have these 5 upward pointing spins. This is important because, if you had just one upward pointing spin, that wouldn't really be remarkable as order because it's just one. To have order, you really need to have a bunch of things that agree to align in their quantum variables. The second is a separation of energy scales. So we're interested in storing information in spin in this example. And so the spin energy gap between, say, 3D upspin and 3D downspin is much smaller than the energy gap between the 3D orbitals and the 4s orbitals. This means that if we want to use some sort of experimental control mechanism to try to switch between 3D up and 3D down, we can do so and move those energy levels around without really worrying about them crossing over with these lower energy levels of the 4s orbitals. So we need to also have this separation of energy scales and have our useful quantum number kind of isolated from the other quantum numbers. And if we combine these two, if we fulfill these two requirements, then we can easily control the valence orbital's order. So in this case, you can use a magnetic field to adjust those up and down spin energy levels and make one favorable or the other without worrying about disturbing all these other orbitals below it and messing up the order. So this is great. This is a useful example, but it's an atomic scale example. To do anything useful with electronics, we need to be able to get order in an entire conducting system. And this is where Landau levels come in. Landau levels are a phenomenon in which you put a two-dimensional material into a perpendicular magnetic field, and you find that the electrons begin to orbit around. Thinking about it just classically, electrons in a perpendicular magnetic field will experience a Lorentz force, and so they'll orbit around, as you see here. What this gives us in the quantum picture is the extra quantum number in terms of the orbit centers. So this has to be something with little or no energy cost. And indeed, it doesn't really matter where the electron is orbiting around. That's not going to affect the energy. So our extra quantum number is the location of the center of the orbit. And then, of course, the useful quantum number with a well-separated energy scale is just going to be spin in the most common examples. And as I'll show as we start to discuss other materials, there are other things that can also be useful quantum numbers for information storage. To examine this a little more closely, let's look at the energy level diagrams of the density of states as we increase magnetic field going to the right with these plots showing energy on the vertical axis and density of states on the horizontal axis. You can see that as we increase the magnetic field, two things happen. One is that these energy levels, these Landau levels, become deeper and deeper. That is, they can hold more and more electrons. They're more and more degenerate. They have more and more of those extra quantum numbers. Thinking back to the classical picture, this makes sense because as you turn up the magnetic field, those orbits become tighter and tighter. And so you can fit more and more of these little orbits inside your material. And hence there's a higher degeneracy, more of these extra labels. And secondly, the different energy levels become further and further separated. This is very useful because, as we said earlier, we also need to have a good separation between the relevant, the useful quantum numbers, the ones we want to store information in, and the other ones that won't be used for information storage. So these density of states diagrams just consider Landau levels themselves. They don't consider spin. So let's add spin back in. When you add spin back in, there's a small split between, say, the upspin and downspin Landau levels for each orbital. So here is orbital 0, up and down spin, orbital 1, up and down spin. And they're, again, well separated, so they're useful for information storage. The way you do this, again, is to adjust the energy levels of each state. So if you fill only one of the topmost Landau levels, then you can control whether upspin or downspin is more energetically favored to control the order of this state. So here, for example, we've adjusted the system with our applied magnetic field so that the upspin state is favorable. And so the system is in an up-ordered state, an up-spin ordered state. You don't have to think about these Landau levels deeper down because the upspin and downspin are filled together. So all those lower levels are simply neutral and don't have any net polarization. And in that way, the polarization of the topmost level controls the order of the system. So this is just 1 degree of freedom. This is just making order with spin. It's all the more interesting if we have more and more of these small splittings between energy levels. And the way you get those is by having symmetries that are only weakly broken. So there's only a small gap between the states. Without a magnetic field, we typically refer to spin as a spin symmetry, because without a magnetic field, spin up and spin down have the same energies. Then when you apply a magnetic field, it weakly breaks the spin symmetry through the Zeeman splitting. Similarly, we're interested to see what other weakly broken symmetries we can have to generate new useful quantum numbers for information storage.
Brett, can we maybe go back and ask one question?
Sure,
Because there's one question on the chat from Itamar. Itamar, I'm not sure if the question was related to this slide, maybe the previous one. Maybe you can unmute yourself.
Asking simply what the colors mean, and what does it mean when there is no color?
Thank you. Thank you for pointing this out. What I am trying to indicate with the colors here is whether a state is filled or not, and what state, what quantum number that state has. So in this picture, I have the red indicating spin up, blue indicating spin down, and white indicating that the state is not filled. So here I'm showing that the n equals 0, in the n equals 0 orbital, both up and down spin states are filled completely. But in the n equals 1 orbital, only the spin up state is filled, while the spin down state is still empty. And that's why in this example, we have a system that has a net orbital order, excuse me, a net spin order with spin polarization up.
Okay, there's one more question from Dev. Dev, maybe you can also unmute yourself and ask.
Yes, go ahead.
Or maybe I can read it.
Yes.
Am I correct? Am I correct about extra quantum number? It's arise due to applied magnetic field.
Yes, that's exactly right. So if we go back to this slide, this is a classical picture, but it's a very good. It provides very good intuition that closely mirrors what happens quantum mechanically. As you apply a magnetic field, thinking classically, the Lorentz force makes these electrons do this little orbit in the plane of the 2D material. And as you turn the magnetic field higher and higher, the orbit becomes tighter and tighter. And as a result, you can fit more and more of these orbits into the material. The quantum number in this case is the location of the orbit, say the center of the orbit. And as a result, as you turn the magnetic field higher and higher, you have you can fit more and more orbits in your sample. So there is a higher and higher number of possible values for this orbit center quantum number.
All right. I don't see more questions now. Yeah, so there's a comment from Itamar that it's spin orbit interaction.
There are some materials where the spin orbit interaction is important. In this case, it's not particularly important. That is in the case of bilayer graphene. it's not a terribly important parameter. And while this classical analogy is very useful for the intuition of the orbit centers, which does loosely hold, it is not exact. So I wouldn't necessarily frame it as these electrons are orbiting, and therefore we should think of a spin-orbit interaction. It depends on, if you want to go into technical detail, there are actually multiple gauges with which you can solve this. And in one, the most common gauge that is used has only the kind of orbit in a single direction and a plane wave in the other direction. Nonetheless, the idea still holds that you can fit more and more of these into the material as you turn up the magnetic field. So I think in this case, the simple answer would be that we shouldn't take this analogy too far, and the spin-orbit interaction doesn't necessarily play the same role as we would think of here.
All right. Do we have more questions now?
Yes.
Yeah, Itamar?
So when when the orbits get, or when the states get tighter and tighter, it is good for the space and packing more information. Is there some room for confusion? Like, can the orbits get mixed up? Sorry for my non-formal expression here, but you know what I mean.
Yes, no, it is a good question. And no, the orbits do not overlap. So the change in length scale also keeps the wave functions more and more tightly localized. So it's not only that the orbits are moving closer together, it's that the states are getting more tightly packed themselves. So, if these are my two wave functions, it's not just that their centers are moving close together, it's that at the same time, the wave functions are becoming more tightly packed. And so they don't overlap and and confuse themselves with one another. Is that what you're asking?
Exactly, thanks.
You're welcome. Thanks for asking.
All right, good. I don't see more questions now, so maybe we can continue, and then if there are more questions, we will interrupt.
Sounds good. Okay, so where we left off was we were discussing how the more and more weakly broken symmetries you have, the more useful, potentially information storing quantum numbers are available to you in your system. And this brings us to bilayer graphene, which I hope to show you is a particularly interesting system because it has 3 different possible quantum numbers that we can store information in. Before getting to bilayer graphene, let's simply start with graphene. You may have heard of this material that was the source of, I think, the 2010, maybe 28 or 2008 Nobel Prize in Physics. It's a simple hexagonal lattice of carbon, single element, perfectly flat material. And you can tile this, you can create this if you think like a condensed matter physicist, what's the smallest possible repeating unit? It's this little diamond or this little rhombus here of with just 2 atoms in it. So if I take this rhombus and I start copying and pasting it, you can see that I can generate the entire hexagonal lattice in this way. So condensed matter physicists tend to think just in terms of the smallest unit, and that contains all the information we need to understand the total system. You see that it still has 2 atoms in it. You can think of it kind of like a right-facing atom and a left-facing atom. So sometimes we also think of these as generating a right-facing lattice of atoms all here, and then a left-facing lattice of atoms all here. And so the last thing you notice is that if I take this and I flip it around 180 degrees, that is, I rotate it like this, it still looks the same. These two carbon atoms are identical. So if we flip it around, we have still the same thing, except that we've now exchanged sublattices. So we say that graphene has a sublattice symmetry. That's good. That's one more symmetry. But we're still on graphene. Now, if we go to bilayer graphene, it's simply one layer of graphene stacked on top of another. And now we have an additional layer symmetry. So if you flip this upside down, now you have the same material. All you've done is switch the top layer with the bottom layer. And so bilayer graphene has these two symmetries, layer symmetry and the sublattice symmetry that inherited from the simple single layer of graphene. Altogether then, bilayer graphene's Landau levels are going to have three weakly broken symmetries. One is spin, another is sublattice, and finally there's layer. So those are our three symmetries that are going to give us three useful quantum numbers for information storage. The spin, of course, just gives us, the up spin and down spin as our two possible quantum labels. The sublattice symmetry gives us a momentum space symmetry. So you have a right moving, hopefully my camera isn't reflected, a right moving a state and a left moving state that have the same energy or have nearly the same energy depending on how we perturb the system, how we probe it with applied fields. Curiously, although the valley symmetry arises due to the sublattice symmetry, it's tied to the layer in that the right moving states tend to live in the upper layer and left moving states tend to live in the lower layer. And I've depicted that here with a right moving state in the upper layer, left moving state in the lower layer. We typically index these with plus for the right moving upper layer state and minus for the lower layer left moving state. And finally, there's the layer symmetry itself, which gives us an orbital degeneracy. This means that two of the Landau levels that we were looking at earlier that were all evenly spaced actually nearly collapse on top of one another. And you can think of the actual physical object in which the information is stored as being the shape of the wave function effectively. So now we have these three binary valued quantum numbers that was combined together to give us 2 by 2 by 2 equals 8 weakly split Landau levels. And what's especially useful in this system is that we can control each of these quantum numbers, not completely independently, but well enough that you can use one field versus another to influence them and affect what the actual ordered state of the system will be. So spin, as we know, spin will align with a magnetic field. So a magnetic field can be used to control the quantum label of spin. And because the two valleys, plus and minus, tend to occupy different layers, the upper layer or the lower layer, you can use an applied electric field that pushes electrons, to whatever layer that electric field points toward as a means of controlling the valley degree of freedom. And finally, what I hope to show with this work is that if you compress the two layers together, that will influence the orbital degree of freedom. So here I've stated again the three quantum numbers that we have: orbital, spin, and valley. And again, we typically label them 0 and 1 for orbital, up and down for spin. and plus and minus for value. And here are the 8 energy levels that we get by combining those three quantum numbers. And here I've shown finally the energies of these Landau levels as we adjust the applied electric field. And you can see that, for example, if I look at 0 plus up and 0 minus up, these are the same state, except that they're in different valleys and hence different layers. And so looking at them here, of course, as I apply electric field, one of them is raised in energy and one of them is lowered in energy. And so what we can do with this phase diagram or with this energy level diagram is we can say, all right, I want to know as I adjust the electric field, for example, what will the ground state be as a function of electric field? And so to compare to experiment, I'll just look at the simplest thing we can check, which is what is the ground state at low electric field? Say I fill half my energy levels up. That's the lowest 4 energy levels. If I look down at this legend for the plot, I see that these are all my orbital 0 states, and all the orbital 1 states are left empty. So if we just look at the Landau levels alone, we don't think about electron-electron interactions, this model would predict that at low magnetic and low electric field, we'll have an orbitally ordered state. So let's keep that in mind for comparing to experiments. Before I actually show experimental results, it's helpful to show exactly how these experiments tend to run. Often we have bilayer graphene in the middle here in dark gray, sandwiched between hexagonal boron nitride dielectrics. And atop that, the loaves of bread for the sandwich are metal gates that we use to apply the electric field. You apply a voltage, a differential voltage between these 2 plates, say positive up here and negative down here, and that's how you apply an electric field. And at the same time, you can do a conductivity or resistivity measurement of the bilayer and see how the conductivity changes as you apply an electric and a magnetic field. Other experiments will do a capacitive measurement where you measure essentially the polarization of the bilayer as you apply the electric magnetic fields. But for now, let's just look at this conductivity measurement. So here, what is plotted is the resistance, or the logarithm of the resistance rather, against the electric field. And what you see is that these different traces that are carried out at different magnetic fields, we have one trough, which then splits into 2. And these resistivity troughs, or equivalently regions or instances of high conductivity, are interpreted as a phase transition. And the reason being that if you have just your entire material in one big insulating phase, then you expect low conductivity. But if you have a phase transition, then the 2 different phases that are being transitioned between will sort of percolate through one another, and you'll be able to have conductivity as these phases percolate through one another. So now we have a magnetic field and an electric field at which we have observed what we believe is a phase transition. So let's plot that in a diagram of magnetic field on the horizontal axis versus electric field on the vertical axis. All these points represent measurements of a resistance trough or a conductivity spike that is interpreted as a phase transition. And these 2 diagrams are, once they're scaled, give the same result through 2 different experiments. So this is a very trustworthy and reliable measurement of where we should be seeing phase transitions. Yes?
Okay, Brett. Yeah, there's one question from Itamar. Itamar, maybe you can unmute. and ask.
Yeah, I'm wondering in a very naive way, once you have magnetic field and electric field together, how Maxwell equations can play here in terms of predictions. And I can go on talking about V cross B if the electron is moving with speed velocity V, and there is V cross B and so on and so on.
Right. So I think that the key here will be that we have to approach this by using the electromagnetic Hamiltonian in quantum mechanics. So instead of entering through Maxwell's equations, the way that we will see the magnetic field entering is through the Hamiltonian, through an adjustment of the canonical momentum. We do actually see a little bit of Maxwell's equations when we look at the Coulomb interaction and the experimental setup here, because we do want to have an interaction kernel that accounts for example, the presence of these gates and the separation between these layers. So the answer is a little bit mixed in we're not treating the Coulomb interaction fully quantum mechanically, like we're not treating it as electron, photon, photon, electron. So we do use Maxwell's equations for that part of the interaction. But as far as the entrance of the magnetic field into the model, it comes in through the canonical momentum in the quantum mechanical Hamiltonian.
Okay, thank you.
Thanks for the question. Okay, so back to these diagrams. These again, we're showing where we see some phase transitions in the plane of electric versus magnetic field. And furthermore, you can use a little bit of more different kinds of experiments to detect what these phases might be. So in particular, you can use a polarization measurement, measuring the polarization of the bilayer to detect when there is a valley ordered state, because a valley ordered state will have all electrons in one layer, and hence there will be a measurable polarization of the bilayer. And in the case of a spin ordered state, there will be an edge conductivity, a quantum Hall edge conductivity, or quantum Hall edge states that give you a conductance along the edge that you can also measure. And through means like that, we're able to detect that the state that's present at high magnetic field, low electric field is a spin ordered state, while at high electric field, lower magnetic field is a valley ordered state. And in between is a state that has some mixed order. It has some partial order in all of the other quantum numbers. So it has a partial spin order, a partial valley order, and also a partial orbital order. But if we compare this back to the simple theoretical model that I had earlier, that had predicted that at low fields, we'd have an orbitally polarized state, an orbitally ordered state. But this doesn't appear anywhere in actual measurements. So if we want to have a useful theoretical model that can be more helpful with our predictions for experiments, then we need to have a bit more substance to it. We need to be able to account for interactions, which must be playing an important role here. I'll pause for a moment and see if there are any other questions before I move on. And if not, then I'll show why we can account for interactions as being a very important factor in this model.
Right. Yeah, I don't see any questions on our chat, but maybe someone would like to unmute. Okay, I think we can move on and we'll interrupt later.
Sounds good. Thank you. Okay, so if we look at the energy scales and how they scale with the magnetic field, it will quickly become apparent to us why we needed interactions. If you look at the Zeeman energy, it's linear in the magnetic field. And similarly, if we calculate the orbital gap, that is the gap between 0 and 1 lambda levels, we find that that energy also varies linearly with the magnetic field. On the other hand, if we look at the interaction energy scale, it scales as a square root of the magnetic field. Simply plot the square root on top of a line, and what you see is that when the argument here, the magnetic field, is low, the square root is the dominating energy scale. And it's only at sufficiently high magnetic fields that there will be a crossover, and the line will start to dominate over the square root. So putting that back in physical terms, what we see is that at lower magnetic fields, the interaction energy scale will be larger than the Landau levels non-interacting energy scale, and only at higher magnetic fields might we expect to see more orbital order, more of the non-interacting energy scale coming into play. So now we know that we need to include interactions more carefully. How are we going to do that? After all, we're talking about a solid state system that has on the order of 10 to the 23rd electrons. The way we do that is through a mean field model. This is the most commonly used model to understand this type of system. What we do is, instead of solving the Schrodinger equation for all of the countless electrons in the system with couplings between them, we substitute in one particle and a density. That is, we calculate only the interaction of one electron with the density generated by the entire collection of electrons. That allows us to include interactions while still having a model that can be solved in a similar way to a single particle model. What does the mean field interaction do to the system? It does two things largely. One is that it adjusts the energies. So you can see, for example, energy level A here goes to a lower energy level D goes to a higher energy. The other is that it can mix states. So the non-interacting B and C states here become mixed into a superposition of a B plus C and a B minus C state. So those are going to be the two main effects of the interaction. It will adjust energy levels, and it might also mix them. And in the mean field, we can also break down the interaction into two terms to better understand it. One is the direct term, and the other is the exchange term. The direct term is a simple Coulomb repulsion. You can think of this purely classically. The electrons are all negatively charged particles. They simply repel one another. So the electron whose motion we're solving for in the Schrodinger equation feels a repulsive interaction with the density of all other electrons. And this adds a penalty because, again, it's repulsive, and so it costs energy for this repulsion to be present. Next is the exchange term. The exchange term is where the interesting quantum mechanical effects come in, and it actually originates from the Pauli exclusion principle. Remember, Pauli doesn't like to have, or actually Pauli forbids electrons to have the same set of quantum numbers. One effect of this is that electrons with the same spin can't be in the same position. And what this does effectively is it provides beneficial interaction that favors states with the same symmetry, so same spin, same valley pairs, for example, and it reduces the energetic penalty there. I'll explain why that happens a little more in depth in the next slides, where I examine the direct and exchange interactions as they apply to bilayer graphene more explicitly. But the overarching idea here is that the total interaction is direct minus exchange, where the electron feels repulsion from the total density, but the repulsion is a bit mitigated for pairs of states that share symmetry. Looking into the direct interaction more carefully for the bilayer specifically, the Coulomb interaction wants to repel electrons, and so what this does is it effectively fights layer polarization. It fights valley polarization. If you have all your electrons crammed into one valley, then they're packed more tightly together than they would be if they were spread across the layers. So the direct interaction tends to fight against valley polarization. It penalizes electrons for crowding into the same valley and hence the same layer. Then the exchange interaction, as I said earlier, doesn't like same spin electrons to be in the same place. Now, this is relevant, this connects to valleys because the only way for electrons to ever be in the same place is if they're in the same valley. That's because valley plus electrons live in the upper layer, valley minus electrons live in the lower layer. So if electrons are in a different valley, they'll never be in the same place and they won't get any benefit from the exchange interaction. So the exchange interaction has the effect of favoring same spin and same valley interactions. It likes it when we fill states that have the same spin or the same valley, or in other words, it favors spin and valley polarized states. Okay, so our big takeaways for the interactions are, first, that the interactions are very important when the magnetic field is lower. Second is that the direct interaction does not like valley polarized states. And third is that the exchange interaction likes spin and valley polarized states. With that, we're ready to start looking into some theoretical results and comparing some models. Before I go into mine, I want to look at some of our predecessors. These largely come into two classes of models. One, where the Coulomb interaction and relevant parameters are derived from basic physics. For example, the Coulomb interaction, as Itamar asked earlier, is derived from the Maxwell's equations. So we take this system where we have the gates and the bilayer and then the dielectric and all that, and we solve Poisson's equation to find out what the Coulomb interaction should look like in this geometry. In the other class, the interaction is assumed to be short range, so it's assumed to be effectively a delta function interaction in position space, and the parameters are chosen in a kind of explorative way, rather than taking a parameter from from a measurement of the dielectric constant of the system or something. The second group explores a range of all possible parameters to kind of create a dictionary of possible states. If we choose these parameters, what might the result be? What phases might we see? And so what do we see as a result of these two explorations? Well, the ones where the interaction is derived predicts a continuous transition from spin to valley. So instead of going suddenly spin ordered, suddenly Valley ordered. What this does is it slowly morphs from spin to Valley order. And wherever this slow morphing appears at all across the full range of magnetic fields. In comparison, the model where the parameters in your interaction form are chosen shows a bifurcation of a sudden transition, so a sudden jump from spin to Valley rather than a smooth transition. And it bifurcates around here into two phase transitions, a sudden jump from a spin order to a mixed order, and then another jump from the mixed order to the Valley order. So each of these models has attractive features, but also drawbacks. The drawback of the derived model is, of course, that the result isn't entirely correct. It doesn't predict the experimental result where we have a single bifurcating phase transition, a single phase transition at lower magnetic field that bifurcates into two phase transitions at higher magnetic field. It does correctly capture the transition from spin order to Valley order, but it doesn't quite get correct what is in the middle. On the other hand, in the model where the interaction parameters are chosen, we do have a result that more closely mimics what we see in experiment. It more closely predicts what we see in experiment. It has the three phases that we expect, and it has the discontinuous jumps that would manifest as conductivity spikes or resistivity troughs, and that's what's experimentally seen. However, because the interaction form and the parameters are simply chosen in a more explorative way, it doesn't quite explain how this interaction or how this phase diagram arises in the first place. If we want to know why, we need to have somewhere in between. We need to have a model that takes the basic physics and then produces an interaction of this form. So that leads to the goal of my work.
Can I ask a question?
Yes, please do.
Yes, I'm not expert on the subjects. I'm an engineer. I'm just wondering, in your graphic that you're showing this a kind of non-linearity. There is a critical point there.
Yes.
Where you get a split.
Yes, right here.
Yeah. So if you conduct your experiment from low magnetic field to high magnetic field, so where you get this bifurcation, and if you do the opposite from higher magnetic field to lower, does the critical point of the bifurcation remain the same or change?
That's a good question. I don't think that there's a change, but I am a theorist and I wasn't part of the experiment. I don't remember there being any sort of hysteresis effect that was discussed. But again, that I'd have to review the relevant papers and see whether they checked for that, and if they did, whether they observed it. But I don't believe so. I have no memory of that offhand.
That's fine. Thank you.
Thanks for asking. That's a good question. Okay, so going off of these two models, the goal of my work was to see if by making some changes, making some refinements of the treatment of the interaction that is derived from known physical principles, we can produce results that are more similar to what is seen in experiments. So the refinements I make can be put into three boxes. First is a non-perturbative treatment of the wave functions for the non-interacting Landau levels. It's common to take simplified models and calculate the interactions analytically, that is, in such a way that you can write the solution down by hand. to get the wave functions that are used in the interaction. In my work, I instead solved the Hamiltonian matrix numerically to get a numerical wave function that is more complex and captures more features than the analytic approximations for the wave function. Secondly, I solved a bit more complex form of the Coulomb interaction kernel. So previous work would, for example, consider a bilayer in free space, or in free space with a dielectric, or it might consider a single layer, neglecting the separation between the graphene layers, and only consider the gates. And so in my work, I combined these two and treated a system where we respected both the presence of the gates and the separation between the graphene layers in the model. And then finally, I addressed the out-of-plane electron density in the bilayers. So thinking back to all the discussion about Landau levels and graphene as two-dimensional systems where everything is flat. Of course, that means that the home of the Landau levels is flat, but the electrons still live in three-dimensional wave functions. It's been common so far to neglect the extent of these three-dimensional wave functions out of the plane of the graphene and just treat it as if the wave function lives purely in the plane. So the final refinement that we made was to treat fully three-dimensional wave functions in our models. Now the results are as follows. We saw similarly to previous parameter-free models with where all the parameters and functional forms of the interaction are derived from basic physics. We saw a spin polarized state at lower electric field and a valley polarized state at higher electric field. And what's occurring here is that the direct interaction fights against valley polarization, and so that the ground state at low electric field is a spin polarized state. But if you turn up the electric field higher and higher, eventually the electric field becomes high enough to override the direct interaction, and the system goes to a valley ordered state. Again, the reason being that valley order is essentially the same as layer order, and so you simply polarize the system, putting all electrons into the same layer, hence the same valley. Well, now what happens if we add some pressure? We compress the layers of the system. This is the new experimental control mechanism that my work aims to explore, in addition to refinements of the interaction. We find that as we apply pressure, 3 new phases move into the model. 2 of them have mixed order. These are the orange and the dark gray states. And 1 has purely orbital order, and this is the light green state. All of them have some amount of partial or complete orbital order. So what we're showing here is that as you apply pressure, it brings in some orbital order. Indeed, if we go to 1 rung higher in the ladder of applied pressure, you can see that these orbitally ordered phases move in further and further to lower and lower magnetic fields. This is interesting to understand, so let's think a bit more about this pressure as a means of controlling the orbital degree of freedom and see how that works. I showed earlier a diagram that showed that the orbital gap, the gap between the 0 and 1 Landau levels, was linear. I didn't discuss much how the slope of that line depends on pressure. If we look at this plot here, you'll see that there's a low slope at low pressure, but as the pressure increases, the slope gets steeper and steeper. Now, when we plot a line with a steepening slope against a square root, you see that as that slope of the line gets steeper and steeper, the point of the crossover moves to lower and lower magnetic fields. That is, if we have a very shallow slope, it will be a long time before the interaction energy scale loses to the non-interacting orbital energy scale. But as we apply pressure, we steepen that line and we make that crossover move earlier and earlier. So here, as we have applied moderate pressure, you say that the crossover is at a moderate magnetic field, and at high pressure, with a very steep slope for the non-interacting energy scale, the crossover occurs at a much lower magnetic field. So let me show this in the form of those plots. Here I'm coloring things by the degree of orbital polarization, with the pale colors being no orbital polarization, the gray being moderate orbital polarization, and the black being full orbital polarization. You can see that if I apply pressure, that is moving rightwards along these diagrams, then the orbital polarization appears at lower and lower magnetic fields as it becomes easier and easier for orbital polarization, that is for the orbital energy scale, to dominate over the interacting energy scale. So that's useful. We've shown that there's one more way that experimenters can control these useful quantum numbers, these spin, Valley, and orbital quantum numbers, and that's by applying pressure to the bilayer. For a quick recap, let me look at a comparison between parameter-free models and see what else has changed. These first two are predecessors to my work that are similar in spirit. They also derived their interaction from basic physics principles. The first one and the second one both have wave functions that are treated as fully two-dimensional. So they did not address the out-of-plane extent of the wave function as happens in my model. And they also used different wave functions, different levels of approximation for the wave functions that were used in the Coulomb interaction. These were both analytically calculated, just with in different forms. And what they both predict is that there is a superposition region where there's a smooth transition from spin to Valley polarization. So here it's quite thin, but there is a blending region between the blue and red, that is between the spin and Valley polarized states. Here it's a bit wider, magenta being a spin, blue, Valley, and orange being the smooth transition region. I apologize for the difference in choice of color schemes here. Whereas in my work, there was no continuous transition. It was a sudden jump from spin-ordered to Valley-ordered states. This could be interpreted as an explanation for why experimenters see a sudden jump, a sudden conductivity peak or resistivity drop in their measurements. That could explain the difference there. But more than that, it shows that even these very fine details of the model, even the very fine details of how we treat the interaction, can be very important, simply because the interaction energy scale is so large and interactions are really controlling the physics in most experimentally relevant parameter regimes. Okay, a summary of what we've done so far with Landau levels in bilayer graphene. We've shown that we can control the spin, valley, and orbital polarizations with applied electric, magnetic, and pressure. With applied electric and magnetic fields and pressure. We've shown that the results hinge upon the fine details of the interaction. And finally, that a full explanation will require further research. We'll need to do a bit more work to be able to bring the derived parameter and chosen parameter models to meet in the middle and find a way to really explain the origin of the parameters that produce these phase diagrams. So that by and large covers the work that I wanted to show you that I had done and that my colleagues' work was based on. But I also want to leave you with some more interesting tidbits from bilayer graphene and from similar materials. So we discussed early on that if you think about the classical picture of a two-dimensional conductor in a magnetic field, the Lorentz force starts putting the charged particles into cyclotron orbits, but we didn't really talk about what happens at the edge. If you have a cyclotron orbit on the edge here, then the electron's going to try to orbit around, and it's going to bounce off the edge, and it's going to keep on moving along and keep on moving along the edge as it continues to bounce, orbit, bounce, orbit, bounce. And so these make some edge states. And moreover, as I'm going to show, you can control the movement of the edge states if you can control the occupied phases. And so some of my experimental colleagues were able to use this to create a beam splitter and valley valve. So that is, they used valley ordered states and controlled the ordering of different regions to make an experimental valley valve and beam splitter. So the setup is shown here in the lower part. You can see that they have 4 gold-colored electrical gates, and by applying different charges to these gates, they can put different regions of the material into a different ordered state. So, for example, you apply a positive charge to this gate, then it might put this into a valley plus ordered state. You apply a negative charge to this gate, and it puts this region of the material into a valley minus ordered state. As a result, you'll have a boundary between the valley plus and valley minus ordered states. And along that boundary flows an edge state. And this edge state continues to follow boundaries between unlike valley polarized states. So for example, let's look at this valley plus polarized state here. It has 2 boundaries with valley minus states. It has a boundary here and a boundary here. So we have an edge state that follows that boundary and curves around to the left, following the boundary again between the valley plus and valley minus ordered states. And if we shift our perspective to this valley minus region, it's got 2 borders with valley plus ordered states here and here. And so an edge state would also follow this border and get diverted this way. So in this way, we have an edge state, a valley edge state that's split among 2 paths. This is what they mean by a valley beam splitter. And simply by changing the way that you've polarized the different regions into different ordered states, you can create the valve configuration. So in this lowermost picture, they've deflected the valley edge state downward by having only a single region of valley down polarized state. And in this case here, they have only a single region of the valley plus ordered state, and they've deflected the valley edge state upwards. So this is the Val configuration, where they're able to control the direction of this edge state by controlling the polarization of the surrounding regions. So that's a nice electronics device if you want to start controlling valley polarized electrons. You can start using a device like this that will direct them accordingly. Earlier, we'd also discussed spintronics, and we discussed the skyrmion. Just as a reminder, a skyrmion was this topological feature where you have a bath of upward pointing spins, say, and you curve those smoothly down so that it's stable, because each spin is closely aligned with its neighboring spin, and yet in the center you still have a different alignment from the bulk. So in the center you have an overall downward direction for the spins in opposition to the bulk upwards. But that's just for spin. You can also have skyrmions that are not simply spin. So already in the early days of Landau levels and bilayer graphene, it's been predicted that you can have valley skyrmions. So you can have isolated but stable regions of an unlike valley. And not only that, but you can also have spin and even orbital skyrmions. So each one of these degrees of freedom, each one of these quantum labels has the option of storing information through these small localized regions. And moreover, you can also pack them together, as you would need to do for information storage, and create sort of a crystal of these skyrmions packed together. I see we have a few messages in the chat though, so I want to pause for that. Okay, looks like
there are some questions about the recording and the slides. So
okay, so we don't need to worry about that then.
Yes.
Okay, so yeah, now we have the skyrmions that we discussed earlier about spin, but now they extend not only to spin but also to valley and to orbital. And lastly, I have colleagues that did an experiment with growing graphene on copper terraces. And so what you see in this diagram here is some steps of copper upon which graphene was grown. And what they found is that when graphene was draped off a step, it formed some ripples, very similar to how if you drape a tablecloth off a round table here, you see these ripples along the edge. But what's this useful for? Well, as it turns out, ripples introduce strain into the graphene. And strain manifests in the Schrodinger equation in the same way as a magnetic field would. So you're effectively making a pseudo-magnetic field simply by straining graphene. The pseudo-magnetic field is depicted here with the blue and red regions. And so, as you see, we have a region of upward pointing a magnetic field, a region of downward pointing magnetic field, and so on. And what this makes is, again, boundaries between states that tend to have propagating states along the boundaries. And more generally, it means that we have a platform to do Landau level-like experiments without necessarily a magnetic field, or with a stronger magnetic field than is experimentally realizable, because the strain can have the strain is predicted to produce pseudomagnetic fields on the order of about 200 Tesla at a maximum. So there's a lot more room for exploration there as well. All right, well, that's everything I wanted to share with you. Just as a recap, we went through why we'd be interested in classical computing with quantum variables. I discussed why Landau levels in bilayer graphene are an interesting solution for this problem, and what they have to offer in terms of many interesting quantum degrees of freedom. I explained why interactions are very important if we want to create a phase diagram that we can use as a sort of roadmap to know how to build different ordered states and how to control these useful quantum numbers for information storage. I shared the results of our model, including both what we've learned from it and what we have work still to do. And finally, I showed you a teaser of a few adjacent topics to this work on different ways that you can start to play with these ordered states now that we have them, and how they might be used for information storage, or other ways that we might be able to generate them. So that concludes what I wanted to share. And if anyone has any questions, I'm happy to take any more now.
Yeah, I have some.
Yes.
First, you mentioned at the very beginning new physics, and there was a lot of new physics here, but would be nice to know what specifically you mean when you say new physics. That's first. The other one is, without throwing names here, I thought that van der Waals may be relevant too. Van der Waals potential and forces and so on. And then in principle, since you have shown the valley, the electric field, the interaction with the magnetic field, and then you invoked pressure, so maybe the new physics is exploring, as you hinted recently, different physics parameters or environments to explore and discover new properties.
Yes, and there's certainly more that you can do to the system to control it than I had time to explore. We have I know of other experiments where they've used different kinds of dielectrics to explore how that affects the phase diagram. And while I only discussed perpendicular magnetic field, perpendicular electric field, there are also adjustments you can make, and an additional phenomenon you can detect if you try using in-plane magnetic fields, in-plane electric fields. So certainly, there are so many parameters and so many degrees of experimental control that there is more than that I have, and there's more to show that I have room for in this work. But yes, there's definitely a lot more to explore there.
This curiosity, at the very beginning, we was talking about the tightly packing of states, layers. So is there a limit to that?
I mean, there's a practical limit, and so we haven't really thought of, or at least I haven't ever seen the need to think of a theoretical one. The practical limit simply being the limit of how strong a magnetic field can we realize in the lab. I think that the highest I've seen used in this work is a little above 30 Teslas. But more generally, from the theoretical perspective, there would be a limit, at least in the type of model that we're using. So I am a condensed matter physicist. We think of solid state systems, and you usually think of quite large systems. And in particular, these tightly packed Landau level wave functions, even though they are tightly packed, are still quite large on the scale of atoms. So we typically can think of atoms as like, blurred together into a continuous sheet of material for the purposes of the quantum mechanical calculations that we're doing. Perhaps that would have to be adjusted if you had so high a magnetic field that your Landau level wave functions were comparable to the size of an atom. But at this point, we're still experimentally well above that limit.
What about the surprising magic angle? Are you looking at this?
We did most of this work before we had thought about the magic angle and twisted graphene. There has also been work on Landau levels and twisted bilayer graphene, but at this point we still saw enough mysteries in the in the straight bilayer with no twist between the layers that we just wanted to focus on that and solve that first.
Okay, great. Thank you.
Yeah, thanks for asking.
All right, good. So Brett, thank you for the great presentation, of course, and answering the questions so far. Do we have more questions?
I've got a small query there.
Yes.
Maybe it's not appropriate. It's an engineering problem. The graphene, the manufacture of graphene is very challenging in a sense in terms of production a pure graphene without defects.
Yes.
So I just wonder how tolerant is the system with in the presence of defects in terms of what you've been describing, the physical behavior of these graphene layers.
Well, you know how theorists are. Theorists like to pretend that there's no such thing as a defect unless we're specifically studying them. So the studies of the Landau level phase diagrams and how these ordered states build up tend to ignore concerns with defects, and that's kind of aligned with experiment, where the experiments on these tend to try to get as clean a sample as possible to do their measurements. So at least both experiment and theory are aligned here in that we're still trying to focus on the cleanest systems that we have. And I would defer to experimentalists to study the possibilities of how defects affect these systems, because right now, again, we still have enough mysteries to explore in the perfectly clean systems that's our focus at the moment.
Yes, fine. Thank you.
Thank you too.
All right. Do we have more questions to Brett? Okay, I don't see more questions on our chat, so I think we can conclude. So Brett, thank you once again for the great presentation and also answering all the questions. So I believe that we've learned a lot. Yeah, we would like to thank everyone for joining today and asking the questions. So we hope to see you next time on our future meetups in April. Great. Thank you and have a good week ahead.
Thank you very much. I appreciate everyone coming. Take care.
Yeah. Thanks. Bye-bye.
Bye.
Bye. Thank you.
Thank you too. Take care.